Chapter 10, Plasticity. In this chapter, we are going to study the behavior of structures when the member behave beyond their yield limit. In the past, we normally assumed that all materials remain linearly elastic, so that you can apply Hooke's law, that kind of things, to do your analysis. But when you see this term, plastic means we enter the yield stage after yielding. We would like to study the behavior of materials, of structures, what happened when they yield. And there are 3 different topics. Topic 10 introduce some fundamental theory. Topic 11, we will move on to analyzing some simple structures, a simple beam element. And then the last one, but the most important one, topic 12. In topic 12, you will study how to use plastic theory to do the analysis for frame and continuous beam. I have uploaded all the notes on Moodle. If you want to know more about 11 and 12, you may go to have a look. At the beginning, let us talk about some basic background. What is plasticity? Plastic behavior of structures. Well, a short review about simply supported beam under pond and mid-span. Everyone should know how to do the analysis for these statically determinant structures. This is a statically determinant structures. Determinant structures mean you can evaluate all the reactions simply using equilibrium conditions. You can find out reactions on both sides. We call that determinant structures. And you can find out the shear force and moment of these structures. In the past, we assumed that the material remained elastic. Elastic means no yielding occurred. What is yielding? You may take a look on the stress strain profile at the bottom. At the left-hand side, at the left-hand corner, I showed you a stress strain profile for materials. In the past, we considered the AB region. Material remain elastic, so you can apply Hooke's law when you're considering these elastic regions. But you can see that beyond certain level, beyond level B, beyond point B, materials start to enter in other status. We call that yielding. In this particular topic, we would like to know what happened when the member enter the yield stage. And beyond point C, theoretically, some may hardening, some material may under softening. Yielding. This is one important topic we are going to consider in this chapter. You may think in this way, when the load at the beginning, when the load becomes relatively small, when the loading P is relatively small, the member is behave elastically. But in case when the loading increase gradually, the stress strain in materials will increase, move from point A to point B and then point C. This is how the stress evolves in a member. In this chapter, we will see how the stress strain evolve in a beam members. You will see later in the next sections. And finally, we will reach our capacity. We will introduce what is so-called the fully plastic conditions. Maybe you have seen this term before when you learned structural steel design. When you learn steel beam design, you have already seen this picture. The whole section yield in tension, in compressions. We will go back to have a short revisions about what is so-called the fully plastic conditions in this chapter. And then we can apply that concept to analyze the collapse law of structures. After reaching the fully plastic conditions, the structures, the member, collapse, fell. And this graph shows you one thing. On the top right-hand corner, I showed you one actual stress strain relationship. How to get this stress strain relationship? You can do a simple tensile test. Maybe you have done the test before in your previous study. Put a steel bar in a universal machine and then pull the steel bar. Then you can get this kind of stress strain profile. This relationship is classical for mild steel. The stress strain behavior for mild steel is quite clear because at the beginning you can see the elastic region. And then point B is our elastic limit. Beyond point B, we enter the yield zone, the yield region. For mild steel, you can normally see a very clear yield conditions between B and point C. Beyond point C, theoretically, the material enter the hardening stage. Hardening stage means they can take higher stress, higher than the yield stress. Yield stress, we normally use Fy to denote yield stress. Y denote the yield. And then up to the level D. Point D is, you can see that point D is the actual maximum stress that the member can suffer, that the material can be suffered. Beyond point D, the material enter the softening stage. Stress decrease. That means they cannot take too much loading. And then at point E, point E is the fracture state. Fracture means the material, the steel bar, break into two pieces, break into two parts, and then collapse, failed. Point E. This is the behavior for a mild steel under tension, a very classical behavior. When you test the other material, for sure you may have different stress strain profile. For mild steel, we normally use this as a sample because it's quite clear. You can see clearly elastic, plastic, hardening, softening. What about the picture on the bottom left-hand corner? This one is idealized stress strain profile. In this chapter, plastic theory, we normally use this idealized stress strain profile, a simplified stress strain profile. How to simplify? We only consider these two green lines. We call it bilinear model. We only consider the elastic region and the plastic region. We ignore the hardening, ignore the softening. We ignore that part to make our analysis more easy and conservative. This model, we call it elasto-perfectly plastic model. Perfectly plastic means we have a horizontal line here, no hardening. Elasto-perfectly plastic model. There are some advantages of using these simplifications. Make our calculation more easy, good approximation, simplify our calculations, and more conservative. More conservative because in reality, the material can take higher stress. We have hardening in reality. So when you do the analysis, ignoring the hardening behavior, actually you are suppressing the strength of the material. That's why the result will be slightly conservative. Remember that we are using this bilinear model, two lines, ignoring hardening, ignoring softening in our discussions. That is about the material behavior. Okay, let's talk about beam in bending. What is the plastic actions for beam in bending element? Very classical profiles again. Suppose we are considering a simply supported beam under point of a misbend, the one that you have seen before. In the past, when you learn the beam behavior, we consider one arbitrary cross sections. Say, for example, I consider the middle cross section because based on my understanding, the misbend is subject to maximum level of bending moment. So I consider this particular section at the misbend. Right? You can, if you're familiar with structure analysis, you can draw the moment diagram, shear force diagram immediately for these structures. Simply supported beam, very, very easy. But anyway, I consider the middle cross section, and I try to study the stress strain profile for the middle sections. A beam, you can make a cut here, and then plot the strain profile, plot the stress profile. That's why we have two pictures at the bottom. The top one is the strain, the bottom one is the stress profile at different loading stage. And then assume that at the beginning, P is relatively small p at the beginning. And then what about our stress strain profile? Strain profile is easy because based on this assumption, remain plane assumption. This one is a very important assumption when you study the beam analysis, beam theory, because we always make this assumption, right? Remain plane assumptions. Some textbooks call this Bernoulli hypothesis, which also mean remain plane assumptions. What is the meaning of this statement? Remain plane. It's mentioned that after bending, the section remain a straight line. A section remain a straight line after bending. This is so-called plain assumptions. When the loading is more, we assume that all the material remain elastic. So the maximum stress lesser than our yield strength, the maximum strength lesser than our yield strength. Similarly, stress is smaller than our yield stress. How to get this relationship? Because we are considering elastic stage at the beginning when loading is small. When material remain elastic, you can use this famous equation, Hooke's law. If you know strength, you can evaluate the stress using Hooke's law through the elastic modulus E. So when strength lesser than yield strength, stress will be also smaller than the yield stress. This is what we have before for elastic stage. This one is classical for stress strength. Stress profile is also a straight line. But when loading increase, it's no longer a small value. When loading increase, material will start to enter their yield state. Say, for example, let's take a look on the strain profile again. The strain profile remains a straight line because of the same assumption. Plain assumptions. Based on this assumption, we assume that the section even is a straight line, even though beyond our yield state. Our strain is now bigger than our yield strength. Start to yield. What about the stress profile? Quite interesting. When we analyze the stress profile of a member of a cross sections, you can see that part of the material yielded. The top and the bottom fibers yield, and the middle region remain elastic. This gives us these shapes. Partially yielded. The top and the bottom fibers yield, reaching the yield stress. While the middle portion remain elastic. This condition we call that elastic plastic, or sometimes we call this elastoplastic. Partially elastic, partially plastic. Based on the first principle, we may also evaluate the moment capacity at this stage. But you can see that part of the material remain elastic at the middle. So theoretically, the loading P can be increased further. It can take more loading. Because we still have some elastic region, we can still apply the loading such that the whole section fully yielded. It comes to the last picture. The last picture, again, when strain greater than the yield strength, the strain profile remains straight line again, even though after yielding, because of the plain assumptions. But what about the stress profile? For the stress profile, whole section yielded, one in compression, one in tension. Whole section yielded. Assume that the material has the same yield strength in both tension and compression, and there's no buckling, no the other special issue. Whole section yielded, one side in compression, the other side in tension. This is so-called the fully plastic condition. Whole section yielded. Based on our previous discussion, we only consider the bilinear model, only consider yield stress without considering hardening. So this is the maximum level the section can be suffered. It cannot take further loading because everything yielded. In the following section, we will review how to find out the corresponding moment of resistance. I think you have already learned how to find out the values. We have a short revision about how to find out the values. Elastic, plastic. One thing, neutral axis. Neutral axis means the level without any elongations after bending. You can take a look on the strain profile. When this member under bending, the top side under compression, the bottom side under tension. The bottom side under tensions mean every fiber is under elongation at the bottom. On the top part, under compressions mean every fiber is under shortening. In between shortening and elongation, there must be a level has no any elongation. Right? There must be one transition level, no elongation, no shortening. This special level, we call that neutral axis. Neutral axis, no any elongation, no shortening. Neutral axis. Sometimes I may simply call this NA for simplicity. and a neutral axis. And this is about the section behavior, stretch string profile. You have to understand how the section evolve, how the string, how the stretch profile change at different loading stage. You may also understand the behavior using this overall picture. This is the moment, curvature, relationship. When you apply loading, evaluate the same section again. Simply support the beam, under pono and mid-span, evaluate the middle sections. When you apply the loading gradually, increase gradually, the moment at the section under consideration will increase from 0 gradually. At the beginning, everything remains elastic, so we have a straight line until reaching our yield limit here. At point B, when the section start to yield it, and then we start to see nonlinear behavior. B and D is nonlinear behavior transition between elastic to our fully plastic conditions. This part, BD, represents this middle elastoplastic region, partially yielded, partially elastic. It gives us a nonlinear behavior between BD. And D is another special value. Beyond D, you can see a horizontal line. Why we have a horizontal line beyond D, level D? Because at point D, the member reached its fully plastic condition, which means this last picture, the last picture here. And the whole section yielded means they cannot take further loading. They cannot take further bending moment. That's why the value remains unchanged horizontally. You can also understand the behavior using this overall moment curvature relationship. If you like, you may also map the previous stretch profile in different regions. Here is the elastic region. Here is the elastoplastic region. And finally is the fully plastic conditions. Oh. This is how a beam section evolves under gradually increasing loading. There is a dashed line link up point B and point D. Same assumption. Quite often for our analysis, we don't want to consider any nonlinear behavior. So we artificially extend this straight line to point C. Adopt so-called the bilinear model again. To simplify our analysis, we ignore the nonlinear behavior. Just use this imaginary point C, so that the member also behave as a bilinear model, two straight line, with the formulation more easy. That's why we have point C over here on the picture. And there are two moments we have to emphasize. My and MP. My is the moment when the member started to yield at the extreme fibers. We call it yield moment. When the extreme fibers start to yield, the corresponding moment is called My, yield moment. On the next slide, we will review how to get this value, My. Another special value is MP. MP is the fully plastic moment. When the whole section yielded, what is the corresponding moment of resistance? We will review how to get the values. This slide shows you how to find out the yield moment based on the elastic behavior. A short revision. I'm sure that you have seen this picture before in the other module, mechanics of materials, at the time when you learned the behavior of member under different actions, torsion, axial force, shear, and moment. You have seen similar things before. This is just a short revision about how to derive the beam formula under elastic conditions. Again, based on the stress and strain profile, we have a strain distribution, strain profile on the left. For beam under bending, assume that we have a neutral axis at this level in purple color. Above the neutral axis, based on this direction of bending moment, above the neutral axis is in compression, below this neutral axis is in tension. Strain profile is a linear profile because plane remain plane assumptions. Assume that maximum strain appeared at the top level. We call that epsilon max. Epsilon x is the strain level at one arbitrary level. At level y, at distance y above our neutral axis. Arbitrary values. Based on similar triangle, you can express epsilon x using our maximum strain level, epsilon max. Using similar triangle, you can correlate epsilon x and epsilon max together easily using similar triangle based on the ring plane assumption. On the right hand side, you can see our stress profile, our stress distributions. Stress distribution is also linear because elastic behavior. We are considering elastic stage. So stress profile remain elastic. How to correlate stress and strain? Within elastic stage, you can correlate stress strain easily using this famous equation, Hooke's law. Hooke's law tells us that stress equal to elastic modulus times strain. There are two stress in the picture. One is sigma x. Sigma x is the stress level at arbitrary level at level y above our neutral axis. Another one is maximum stress, sigma max. Maximum stress occurred normally at the extreme fibers, maybe the top, maybe the bottom. And then based on our previous formula, we can replace strain, epsilon x, using our maximum values, epsilon max. And then gamma modulus times the stress give you the maximum stress, sigma m, sigma max. So it seems that we can express our stress using the maximum value. We can express our stress and strain at different level using the maximum value based on similar triangle. This is what we observe from the linear profile. What about moment? We want to know the moment resistance. How to find a moment? Well, you can recall our first principle in the past, how we derived the equation to evaluate moment. We consider a small element, right? Say, for example, I consider this small element in the cross sections. I isolate this small element out. This small element is under a force. What is the force acting on this small element? According to our theory, force is equal to stress times area. Maybe I call this F, dF. The force acting on this small element, theoretically, it is equal to the stress times the corresponding small area, dA. How to find a moment? By definition, moment is equal to force times the moment arm. Maybe I use Y as moment arm because this level is, maybe I said that this level is equal to Y above the neutral axis. This is the moment due to the small element under considerations. Then what about the overall moment for the whole section? The moment for the whole section is equal to summation of the effect for all the small elements along the section under consideration. When you consider all small elements along this section, add up their effect together. This becomes the overall moment acting along the whole sections. Add up the contributions mean integrations. Integrate means summation, right? Integrations mean summations. Add up all the contributions together. So you can write down the formula in this way. Moment is equal to integrations, sigma x times dA. Sigma x times dA is equal to the force, right, dF. F times the moment arm, y. And then integrate along the whole sections. This is the meaning of the formula. And then slightly rearrange the equation. Replace sigma x using the maximum stress, sigma m over c. C is the distance between the neutral axis to the extreme fiber. And then we have one integral, y squared dA. What is this term? According to our theory, this is so-called the moment of inertia, I. This is how we can define this nice number I. We call that moment of inertia. Some textbooks call this moment of inertia. Some call this second order of area. A second moment of area. Slightly rearrange this formula again. Then you can express stress using moment. Y? Y is the level between neutral axis and the level under considerations over moment of inertia, I. In the past, we call this beam formula, or beam formula. This is how you can find out the bending stress based on the internal moment, based on the level Y, based on the moment of inertia. We have seen this formula before in mechanics of materials theory modules. And then what is the last one? The last one is finding out our yield moment. What is yield moment? Yield moment means this one, the moment when the member just yield. When the member just entered the yield stage, the stress profile is still linear when the member just reached the yield state, right? But the extreme fiber is equal to the yield stress or yield strength. The middle one remains elastic. That's why the stress profile is still elastic, even though you enter the just yield conditions, point B. Only the top or the bottom level yielded. We can apply Hooke's law again at this stage. If you can apply Hooke's law, means you can use this formula. This one. You can use this formula to find out our corresponding yield moment. Set the stress equal to our yield value. Rearrange the formula, then you can find out the equation for yield moment. Yield moment, My, is equal to the yield stress times I over Y, yield moment. We have seen this formula in your structural steel design in the other manner, something like that. Y equal to, in your steel design, you use Py to denote the yield stress, the design strength of steel. How to find out design strength of steel? You have to go back to the steel code from the table, right? Depends on the steel grade, depends on the steel thickness, the steel plate thickness, times Z. Z is the elastic modulus. From this formula, you can see what is so-called elastic modulus. Elastic modulus depends on your cross-sectional property, moment of inertia, and the depth of the member. You can derive the design equation based on this kind of principle. Z is elastic modulus, the yield moment. When the member just enters the yield conditions, sometimes we don't want fully plastic condition occurred in the member. In that case, then this becomes one important value to see whether we have yielding or not. Elastic behavior. When the loading increases further, the section will enter the elastoplastic conditions, partially yielded, partially elastic. And it brings up this picture again. Partially yield. Normally, yielding occurred on the extreme fiber, here and here. Yielded. The middle region remains elastic. Based on the same theory, you can use force times moment arm, find out the moment of resistance, if you like. This one just for the reference, not for our exam. Just for reference for these conditions. This gives us a nonlinear behavior. Because to be honest, we don't need to know what happened between the transition between point B and point D. We just need to know point B and point D. We just want to know the yield moment and the maximum plus moment. We don't need to know what happened in between. They are not for design purpose. Unless you want to plot this picture, plot these actual diagrams. Otherwise, the middle part, this nonlinear part, is not very important. If you like, you may have a look of this portion. Partially yielded, we call it elastoplastic conditions. Partially yielded, partially elastic. The last one is also important. Plastic moment. Plastic moments mean the maximum, the true maximum moment the section can be resisted. The whole section yielded. Use one trapezoidal shape as an example. Assume that we entered the fully plastic conditions. That means the whole section yielded. The top part yielded. In compression, For example, the bottom part yielded in tension. Assume that they have the same yield stress. So you will see two rectangles because both are yielded. And then how to find out the corresponding moment of resistance? Let me have a look at the force first. Force. At the top, we have a compression force. When you integrate this stress block will give you one compression force. If you integrate the bottom stress block, it will give you a tension force. By force equilibrium, section force equilibrium, the net force for this cross section must be equal to 0. Right? We don't have net force. We are talking about static right now, not dynamics. You never see a beam rotating, right? That means there is no any resulting force. T equal to C. You can set this equation, section equilibrium. How to find out the total tensions at the bottom? Stress times the area for the bottom section. Assume that the bottom area is equal to AT. Then how to find out the compression on the top? Same principle, right? Assume that the area on the top is AC. So the total compression is equal to stress, yield stress, times the compression area, AC. By simple elimination, you can see that the compression area must be equal to the tension area. So if the total area is equal to A, AC is equal to A over 2, AT is equal to A over 2. That's why I put this value at the beginning, based on section equilibrium. Half of the area in compression, half of the area in tension, based on this resultant force, based on this section force equilibrium. So compression or tension is simply equal to our yield stress times half of the area. A is the total area of the whole section. Okay, this is how you can get the values, get the relationship for C or T. Last one, and the most important one, our plastic moment, or you may call this ultimate moment, because this is the maximum values. MP, how to find out force? Force is equal to, moment is equal to force times the moment arm. Here I use another symbol, Y bar C, for the moment arm, for our compression force, Y bar T to represent the moment arm for our tension force. Okay, so what is the moment? What is the total moment? The total moment is equal to compression force times our compression moment arm plus the tension force times our moment arm on tension side. Simple addition. Add up the contribution on the top and at the bottom. And then you can simplify the equation a little bit. Finally, you can get this expression. Plus moment is equal to our yield stress times A over 2 times Y bar C plus Y bar T. Normally, we group this part together. We group this geometric parameter. We group these geometric terms, A over 2 times Y bar C plus Y bar T, together into another part called S. S is called plastic modulus. In your steel design, you have seen this equation again. Plastic moment is equal to your design strength times another modulus, C, S, right? We call that plastic modulus. This one is the formula you use in your steel design when it is a class 1 section. I hope you still remember what is so-called class 1 section or class 2 section for steel design. If you forget, please go back to review how to do steel design. Okay. I will not ask you in exam, don't worry, but I think it's good to remember some important things. You can use this formula for class 1 section, class 2 section, in which the local place buckling is not quite severe. Right? Otherwise, if local place buckling is quite important, then we divide that as class 3 or class 4 section. For class 3, class 4 section, they cannot develop this fully plastic moment. Anyway, this is how to derive the formula. You know how to find out MP and MY. You have one term called shake factor. Shake factor is nothing but just taking the ratio between the plastic moment and the yield moment. Different cross-section had different shake factor. Say, for example, for rectangular cross-section. For rectangular cross-section, the shake factor is approximately equal to 1.5. You can prove this yourself. You can find out the yield moment and plastic moment for rectangular section yourself and double check this table. For I section, the shake factor is approximately equal to 1 point something, 1.1 to 1.2. Again, if you have time, you may double check yourself. Shake factor, just for your reference. In this module, you have to know how to find out plastic moment and yield moment. I think that's good enough. So the plastic moment depends on two things: the yield value, the yield stress, and second, the geometry of the beam, reflected using these equations. One simple question. Suppose we have an I section. Try to find out the plastic moment capacity for this I section using the previous theory. Assume that the yield stress is equal to 460 MPa. Okay, this is a very simple question. Find out the plastic moment, MP, for this kind of I section. Make sure that you know how to do these kind of calculations. Pretty straightforward. I give you all the dimensions. The width for the flange. This is called flange, right? The width of the flange is 200. The thickness is 40. Red is the middle vertical plate. Red region, the height is 400. The thickness is 40. The flange at the bottom, same as the top. How to do the calculations for MP? Plastic moment. You may divide the section into two parts. You may divide this I section into two parts. One is the flange part. The other one is the red part. And you can see that I just consider the top half region. I just consider the top half. I ignore the bottom half. The reason is very simple, because this section is symmetrical about the middle bending axis. That's why I just need to consider one half. Once you finish the calculation for the top half, multiply the value by 2. Then it gives you the result for the whole section. For symmetric sections, you may use this kind of shortcut. Just consider 1/2 of the cross section. Based on our terminology, I use Y bar to denote the center of the force, the moment arm of the force. We divide the calculation into two elements, the horizontal flange and this vertical web. The thickness, I think the thickness here is equal to 40 mm. The thickness for the flange, for the web is also equal to 40. The height, 200, am I right? Let me double check. Yes, 200 mm. You can put down the geometry dimensions on the picture. And then based on our calculations, we can evaluate plastic moment first. We can evaluate plastic modulus first, S. If you know the plastic modulus, S times yield strength give you back the plastic moment, MP. So firstly, you can evaluate our plastic modulus. Take a look on the equations. At the beginning, we have our number 2. These two represent we have symmetric cross sections. We need to multiply the answer by 2 so that it becomes one whole section. That's why we have a 2 here for the symmetric properties. And then calculate the area. The equation for S is like this. Area times the corresponding moment arm, right? So I evaluate area and moment arm element by element. The first part here, 200 times 40 is area 1. Area 1 for the top flange. Maybe I call this AC1 times the corresponding moment arm y bar C1, something like that. The moment arm is equal to 200 plus half of our thickness, because we measure the moment arm at the middle of this flange. So we have to plus a small number 20 mm. 200 plus 20 gives you back the moment arm YC1. And then consider the second element, the red region. Area AC2. The height of this vertical wrap is 200 times the thickness 40, give you back the area, times the moment arm y bar C2. Moment arm is measured at the bending axis, mutual axis, up to the middle of this vertical wrap region. So it is equal to 100, 1/2 of 200. Put them into our calculator carefully. Remember, multiply this bracket by 2, because in our calculation, we just consider the top half. We have to double the value so that it represents the whole section. And put all the values into our calculator, then we can get this number, 0.00512, blah, blah, blah. S, plastic modulus. And then go back to the previous page, find out the corresponding yield stress. Yield stress is equal to 460. Suppose we have this stress. Stress times plastic modulus give you back the moment capacity, plastic moment, 2000 something. Assume that we consider this elastoplastic model, bilinear model. Quite a simple calculations. But make sure that you know how to finish the calculations. Some new terms. Plastic hinge. Assume that we have a very nice sections in which the section can reach the fully plastic moment. When the section reaches its fully plastic moment, that section can free to rotate without any increase in moment. Just like this picture. This picture on the left shows you the moment curvature relationship. You can see that after the formation of plastic hinge here, the section can free to rotate without increase in our bending moment. This idea just like a hinge. What is hinge? Hinge something like the pin support, something like that. In the past, if you have a real hinge is free to rotate, just like the bottom, just like the picture at the bottom, free to rotate at the hinge level. You can increase the rotation angle without any moment. But what about plastic? What about beam under plastic conditions? Right here. At the beginning, the member is not free to rotate because everything remains elastic. Remain elastic means we have stiffness, we have resistance against the motion. But when plastic hinge form, plastic hinge means fully plastic conditions. When one particular cross section, for example, here, ridge is fully plastic conditions. The whole section yielded. That means they cannot take further loading. It's free to rotate. So when you plot the moment rotation graph for this hinge, for this cross section, it will be something like this. After reaching the plastic moment, This section is free to rotate without any increase in our moment. The behavior, you can compare our plastic problem and our real actual hinge. You can see that in some sense they are quite similar. You can see this horizontal region free to rotate. The only difference is that a real physical hinge can start to rotate at the beginning. Plastic hinge need to firstly reach its plastic moment. After that, free to rotate, just like a hinge. For this case, we give them a special name. We call that plastic hinge. Plastic hinge. After reaching the plastic moment, the cross-section behaves as a hinge, free to rotate. We call that plastic hinge. Okay, a new term for you. And from this picture, you can see one requirement to form plastic hinge. The requirement is that the member need to able to undergo this large rotation. Okay, the member need to be ductile enough to under this large rotation beyond plastic conditions. Not all the member can do this. As I mentioned before, for steel beam, I section, for steel beam, only class 1 section can achieve this behavior. Right? For RC structures, you normally need to check the reinforcement ratio. Right? We have some reinforcement ratio for RC beam sections. You need to make sure that the steel ratio is below some limit. We have a maximum steel ratio. Beyond that maximum ratio, the member become brittle, not ductile. So not all the members can form this kind of plastic hinge. When we assume that in this chapter, we assume that the section is good enough to under plastic moment, good enough to under that large rotation. Okay, otherwise we have nothing to discuss. And other terms is called plastic collapse. Plastic collapse. Plastic collapse means we have formed several plastic hinge so that the member become unstable. Unstable means when we increase the loading slightly, little change in our loading will cause large displacement increment. We call that unstable. In this case, we call it plastic collapse. Just like this picture. Assume that we have three plastic, we have one fixed end beam. And after the formation of three plastic hinge, one at point A, one at point C, one at point B, after formation of three plastic hinges, and you can see that when the loading P increase slightly, the member will deform without too much restrictions. Oh. The member will be deformed without any restrictions, free to move downward. Okay, just like a simply supported beam. For simply supported beam, if you add one internal hinge at the middle, then it becomes unstable, right? Free to display downward. Similar behavior, we call that plastic collapse. After the formation of sufficient plastic hinge, it will make the structure become unstable, free to display. You don't want your structure to behave in this manner, right? You don't want the beam suddenly move down without any restrictions. No good. So we call that collapse, plastic collapse, due to the formation of plastic hinge. This one is one important concept because in our plastic theory, in our plastic analysis, we are going to find out the collapse law based on this kind of collapse pattern, formation of plastic hinge. There are some assumptions to achieve these plastic collapse conditions. As I mentioned before, we consider bilinear model. We ignore hardening, we ignore softening. We consider bilinear model, only consider the yielding. And we use the small deformation theory, assume that the deformation is still relatively small, so that we can ignore the large deformation behavior. And finally, we don't have the other phenomenon, like we don't have buckling, we don't have fatigue, we don't have fracture, we don't have that kind of the other phenomenon. Otherwise, they cannot form the plastic hinge, just like steel class 3 sections. If local place buckling is critical, then the cross section cannot form plastic hinge. If the section cannot form plastic hinge, then there is no plastic collapse. Plastic collapse is related to plastic hinge formations. These are the assumptions for our theory here. Plastic analysis. Based on the previous discussions, we observed that failure of member is somehow related to the formation of plastic hinge, just like here. So we can start from the other side. Normally, in the past, when you want to find out the collapse load of structures, normally, in the past, you assume that maybe you have low loading at the beginning, increase the loading gradually to see where we have plastic hinge form in the section, and then we study the behavior gradually until reaching the plastic condition. This is what we discussed this is what we consider in the past, consider at the beginning. But once you understand plastic collapse mechanism, you can start from the other side. Instead of gradually tracing the behavior of a member, you can directly assign plastic hinge in your structures, in your member, at some critical positions. Directly assign plastic hinge at some critical positions until the section becomes unstable, reaching the so-called plastic collapse conditions. You can do the analysis in this way, without detailedly tracing the behavior. We can directly assign plastic hinge on the member. Just like this example, suppose we have a fixed end beam under Pono, right here. Instead of finding out the moment diffraction gradually at different loading stage, you can directly put plastic hinge in the cross section, because we notice that when the member collapses, we must see some plastic hinge in the member. Maybe firstly, I assume that plastic hinge form at here. Just assumption, okay, just assumption. Assume plastic hinge form at one support. Take a look on the force displacement diagrams at the bottom. Before formation of plastic hinge, everything remains elastic. So expect you will see a straight line before formation of plastic hinge. After formation of the first plastic hinge, we have another straight line, but you can see that the slope decrease. Slope decrease means the member is the stiffness of the member decrease. Right? The slope means the force displacement relationship, which means stiffness. After formation of our plastic hinge, the stiffness decrease. It makes sense because it's more flexible after the formation of one plastic hinge. Then assume, but you can see that the member is still okay. So the loading can increase further. If the loading increase further, we expect that there may be another plastic hinge form. Say, for example, I just assume arbitrarily. Assume that we have plastic hinge form on the other end. Onto. After formation of the other plastic hinge, it's still okay, but the slope even smaller. Until the formation of the third plastic hinge. At the location of the third plastic hinge formed, and you see this three hinge arrangement. Normally, for a beam with these three hinges, it will become unstable because when you increase the loading slightly, the member can deform in downward direction without any big restrictions. Okay. After formation of three plastic hinge, it seems that the members start to unstable. We can also take a look on our force displacement diagram. After formation of three plastic hinges, we have a horizontal line. This means what? This means this beam, this fixed end beam, can deform along downward direction without increase in loading. That means when you keep the loading here, the member will keep settled, right? Collapse, right, for sure. This is how you can do the analysis. We call it plastic analysis. Instead of chasing the moment force, moment shear, moment displacement at different stages, you can directly assign plastic hinge at some selected cross sections, selected positions, and then try your best to find out what happened at collapse. At collapse, we call that mechanism. Find out the failure mechanism of the member of the structures. Based on these failure configurations, you can backward evaluate the collapse law. How much forces is required to make the structure fail in this particular conditions. This is so-called plastic analysis. We will discuss how to do it in the next topic, topic 11, and also the last topic, topic 12. Quite easy, as compared with Siebert's method and structural dynamics. This one is pretty straightforward. Before closing this PowerPoint, we have one last concept about theorems of plasticity. This one just gives you the overall view about how to conduct plastic analysis. We will discuss in detail about how to actually perform the calculation later in the next PowerPoint, topic 11. Sometimes we call it limit analysis. There are totally 3 theories under this limit analysis. Theory 1, and also the most important one, upper bound theorem. Upper bound theorem. Upper bound theorem only consider the collapse state of a member. As I mentioned before, you can directly assign plastic hinge at some critical positions. Based on this collapse mechanism, we try our best to find out the collapse flow using virtual work balance energy. We seldom consider this term before, but later in the next sections, we will discuss how to use this balance work principle to find out the collapse flow. Very, very easy for energy, because energy work is a scalar, not a vector. So you will not see matrix again, only one simple equations. Then it will help you to estimate the loading. But why we call this upper bound theorem? When you apply upper bound theorem, you don't need to use force equilibrium. You just consider the work balance. Normally, if you ignore equilibrium, the result will be overestimated, bigger than the actual value. So we call this upper bound theorem. If you consider failure mechanism without considering equilibrium, then the result will be higher than the actual value. So we call this upper bound theorem. Not conservative, but the calculation is very, very fast, very, very straightforward. But sometimes you have to do some try and error, because you have to estimate, you have to guess the critical positions with plastic hinge. So maybe you have to try different patterns and then apply this energy balance equation based on different situations and the considerations, and then find out the smallest values among all solutions. We will practice how to do it in the next PowerPoint. This is the energy balance equation. On the left-hand side, this is the internal energy. On the right-hand side, this is the external work done. In the next PowerPoint, I will show you how to set up the equations here, just for your reference. Another theorem is lower bound theorem. Lower bound theorem, as reflected by the name, this theorem gives you the lower bound of the solution. Lower bound means the value obtained from this theorem is smaller than the actual value. The value obtained from this theorem is smaller than the actual value. That's why we call that lower bound theorem. For lower bound theorem, this time you consider equilibrium. About the failure mechanism, you are not necessary to consider the actual failure mechanism. So it gives us lower bound solutions. This calculation is not quite important in this module, because actually we have covered already at the beginning in Siebert's method. This method requires the use of equilibrium, find out the moment diagrams, shear diagram. We have already discussed in Siebert's method. So I will not test you again in this particular plastic theory, because I will test you in Siebert's method, not here. You have to try your best to find out the moment diagram if you want to use this lower bound theorem, which is what you've done before. Right. If you have the beam element, then you can use Siebert's method to find out the reactions, unknown displacement, and then finally use the result, plot the moment diagrams, same as before. But you have to impose some new condition to find out the values sometimes. Lower bound theorem. In this module, upper bound theorem is more important. So I will let you know how to apply upper bound theorem in different scenarios in the following 2 PowerPoints. in details. The last one, uniqueness theorem. Uniqueness theorem means you consider all the conditions. You consider equilibrium, you consider the collapse pattern, consider all factors. If you consider all factors, collapse mechanism, equilibrium, everything, then for sure it will give you the exact value. This idea is called uniqueness theorem. But this one is also quite difficult to do the analysis because there are too many constraints. You have to consider too many factors together.